This is a model I built to study one of the most fascinating structures in the human body. It took me nearly 5 years to understand how it works and how to turn that understanding into a mathematical simulation. You may have the wrong idea about how the vocal folds actually work. Most people imagine they're simply opening and closing driven by muscles. They're not. In this video, we'll cover the real physics behind human speech, and then I'll show you how engineers represent the behavioral mathematically using fluid structure interaction, the same approach I used for my project. We have already established that the muscles aren't what directly make the vocal folds vibrate. Their job is much simpler. They position the vocal folds and adjust their tension. But before we zoom into the vocal folds themselves, let's step back and look at the entire system. So here's the vocal folds. And here is your vocal tract. When the vocal folds vibrate, they don't produce speech by themselves. They produce a sound source. That sound then travels through the vocal tract, where your tongue, lips, jaw, and soft palate continuously change the shape of the cavity, filtering that sound into the words you're hearing right now. So the sound coming from the vocal fold, take this shape for example, frequencies, and here is the amplitudes of the frequencies. The vocal tract takes that sound source and amplifies it. It amplifies it, maybe something like this. It may amplify specific frequencies and reduce another frequencies, so a specific sound is produced, for example, like the ah sound. This is an MRI footage of the person talking. Notice how the cavity changes.
There are times in life words fall short.
Each cavity is responsible for a specific filtering that results in a specific sound. So speech is really a two-stage process. First, the vocal folds generate the source of the sound, and then the vocal tract sculpts that source into language. That naturally raises the next question: how do the vocal folds generate that sound in the first place? Instead of muscles repeatedly opening and closing them, air from the lung pushes against the vocal folds until they separate, and air rushes through the narrow opening. The pressure changes, and together with the elasticity of the tissue, and this is very important, a specific elasticity is responsible for this phenomenon. That elasticity causes them to move back again. The cycle repeats hundreds of times every second, creating a stable vibration without the muscle driving every individual movement. In physics, this phenomena is known as self-oscillation. One of the researchers who had made enormous contribution to explaining and advancing this theory is Tits, whose work on the Myoelastic-Aerodynamic Theory in speech had made a huge influence in the field and in my project. In particular, his published commentary on the theory gave me the physical understanding I needed to build my fluid structure interaction simulation and reproduce these oscillations computationally. Now imagine trying to teach a computer to reproduce this entire process. Not just the movement of the tissue or the airflow, but the continuous interaction between both. So since the fluid domain and the solid domain are continuously influencing on each other, we need what we call a fluid structure interaction or FSI simulation. And instead of solving a single physical problem, FSI couples two different worlds together. The airflow is described by the Navier-Stokes equation, while the vocal folds are described by the equations of solid mechanics, using any material model like the elastic one or viscoelastic one, depending on your assumptions. At every instant, the fluid pushes on the structure and the structure deforms, and that new deformation changes the fluid again. We have mentioned the equations at a different video. I will be linking the video into the second. This continuous feedback is called a two-way or coupled FSI simulation, and it's what allows us to reproduce the self-oscillation we saw earlier. To build this model, I imported the geometry of the vocal folds, define the material properties, specify the airflow or the boundary conditions based on the physiological conditions we have, so that's the airflow of the lung, and coupled both physics together. The difficult part wasn't creating the model, it was making it behave like a real vocal fold. I spent almost 2 months adjusting the boundary conditions until the simulation finally started oscillating on its own. Watching those first stable oscillations appear on the screen was one of the most rewarding moments of the entire project. This is an actual footage of the first ever result I got in 2023. It's a wave propagating from the beginning of the vocal fold to the end of it. Look, how was that? So the mode shape has to The cross-section I used for the vocal fold is well known as the M5 configuration, although I modified the geometry for reasons specific to my research question. That's a story for another video. If you're interested, I'll leave a link to the preprint of my research in the description, where you can explore the complete methodology and results. When I started this project, I thought I was simply building an artificial vocal fold. But by the end, I realized I was really trying to understand one of the most elegant physical phenomena in the human body. What looks like simple vibration is actually the result of airflow, tissue mechanics, and their continuous interaction, a problem that took decades of scientific research to understand and months to work to reproduce in a computer. For me, that's what makes simulation so fascinating. Simulation isn't just colorful animation or impression graphics. It's our attempt to translate nature into mathematics, and then mathematics into something a computer can understand. If you'd like to explore the technical details, I'll leave a link to my preprint in the description. And if you enjoy learning how engineers simulate the human body, from blood flow to cancer to vocal folds, consider subscribing, because that's exactly what this channel is about. Thank you for watching, and I'll see you in the next simulation.